Hi, my name is Miles Turner, and I'll be presenting the Solar Power Satellite Builder concept, which has been worked on by Carson Coursey, Ethan Sinclair, Thomas Rodriguez, and I under the advisement of Dr. Brian Gunter. So to give you a brief overview of what we'll be covering in this presentation, I'll first introduce what a solar power satellite is, and then I'll discuss about modularly developing and constructing a solar power satellite. Then I'll discuss the small satellites used in the modular development, followed by a concept of operations, and then I'll talk about a low Earth orbit case study to help provide context on the cost and CO2 footprint associated with using this concept. So to start, a solar power satellite is a large space structure that orbits Earth and collects solar energy. Then, using millimeter or microwaves, the collected energy is then transferred to some ground location for consumer use. These satellites have been conceptualized for many years due to their ability to provide renewable energy, but there's still many challenges with trying to operate one. One challenge is the construction. That being said, in this presentation, my team and I have explored the concept of building a solar power satellite through modular development techniques and small satellites that can construct and maintain a solar power satellite through semi-autonomous assembly. The modular assembly method we decided to use is called the free flyer assembly method. This incorporates sending up loads of small satellites, which we call builder satellites, that can operate as independent spacecraft. The idea being that each builder satellite can maneuver in space in coordination with other builder satellites and then connect to each other to form a large space structure, i.e. a solar power satellite. This technique does have a few requirements, one being that each builder satellite needs flight critical systems, and the other being that each builder satellite needs to have its own specific degree of intelligence. While this method may seem complex, there are many benefits such as the cost of building a solar power satellite can be spread out over time. The maintenance of the solar power satellite can be completed by sending up builder satellites using rideshare opportunities, and that the solar power satellite can actively manipulate its design due to large space structures being built out of smaller independent spacecraft. Here you can see an example of a builder satellite we have designed. The approximate cost of this builder satellite is thought to be about $250,000, which includes the satellite's base systems to operate as an independent spacecraft. This satellite's price could vary, though, depending on the interchangeable specialized systems needed for building a solar power satellite, i.e. the uses of mirrors, solar panels, and energy transmitters. One novel system to point out on this design is the use of 4 electromagnets. As mentioned in the prior slide, we as a team are currently researching the use of electromagnets and their capabilities to help build large space structures, such as the solar power satellite. We believe that by using electromagnets, we'll reduce the dependency on heavy and expensive and complex precision sensors and thrusters commonly used when trying to assemble spacecraft together. We also believe that this will give us an ability to repel spacecraft from one another when we're trying to disassemble or maintain a large space structure. And there's a potential of offering inductive coupling so that energy transfers can be made wirelessly across a large space structure without the need for hardwire connections. Here you can see the concept of operation on how these builder satellites will construct a large space structure. First, dedicated launches send up large number of builder satellites. Once in space, the builder satellites will then deploy their electromagnets and maneuver in orbit to assemble the desired large space structure. After assembly, the specialized systems attached to the builder satellite will then deploy, and the structure will then perform its design purpose. For the case of a solar power satellite, these specialized systems could be solar panels, mirrors, or energy transmitters. Additional launches could be used for future expansion of the large space structures, and rideshare launches could be incorporated as well to help send up individual builders to replace defunct satellites in the structure. To help visualize the ConOps further, here's a video in which we simulate an 18 by 1 by 1 array of builder satellites, transform into 2 3 by 3 by 1 array of builder satellites to show dynamically how the builder satellites will maneuver and connect in space to form 2 independent space structures. We as a team decided to perform a case study analyzing the building of a single solar power satellite at low Earth orbit using the builder concept. From our calculations, the single solar power satellite would have an approximate surface area of 1,000 meters squared, requiring 450 builder satellites, with each builder satellite equipped with solar panels and energy transmitters. We are considering to build the solar power satellite at low Earth orbit since the power relay distance will be smaller, leading to less losses in the energy transfer, as well as more satellites can be delivered to a low Earth orbit on a shorter timeline and at a lower cost per satellite than at other orbits. There's also the added ability of being able to use the rideshare opportunity mentioned earlier. For the case study, we mainly focused on the CO2 footprint and costs associated during the launch phase of building our one solar power satellite, since this phase is the largest contributor to our total CO2 footprint and costs. Our assumed solar power satellite will be built at an altitude of 1,500 kilometers, and we'll be delivering builders using a Falcon 9 rocket. With the current specification of mass and size of each builder, it'll take about 4 Falcon 9 launches, with each rocket carrying approximately 115 builder satellites. The average Falcon 9 launch is responsible for 400 metric tons of CO2 and costs $62 million. The total CO2 footprint would be about 1,600 metric tons, and the total cost would be about $363 million to build our proposed solar power satellite. Now that we have an idea of the total CO2 footprint and cost associated with building our proposed solar power satellite, we can now discuss how to calculate the total energy our one solar power satellite will generate and how much CO2 it will offset. Using the solar constant, which is the amount of energy that can be received at the Earth's atmosphere on a surface oriented normal to the sun's rays, and the total energy transfer efficiencies outlined in the table to the right, the total power received on a ground location is about 100 kilowatts per hour using silicon solar cells, or 221 kilowatts per hour using gallium arsenide solar cells. This equates to a CO2 offset of about 40 kilograms per hour using silicon solar cells, or 90 kilograms per hour using gallium arsenide solar cells. The total CO2 offset is found by using the total power generated by a solar power satellite and using the average amount of CO2 generated per kilowatt hour as stated by the Department of Energy in the United States. Here on this slide, you can see a plot that represents the total power received on Earth as a function of the total number of solar power satellites in space. To provide context, by building one solar power satellite, enough power would be generated in 1 hour of direct sunlight to power one U.S. home per day. By building 4 solar power satellites using gallium arsenide solar cells, it would be possible to generate enough power in 1 hour of direct sunlight to power one U.S. home per month. In the case of silicon solar cells, you would need about 8 solar power stations. Then, finally, you can see that if you were to build 8 solar power satellites using gallium arsenide solar cells, you'd be able to generate enough power in 1 hour to power the Sydney Opera House for at least one whole year. Similarly, on this slide, you can see a plot that represents the total CO2 offset as a function of the total number of solar power satellites in space. You can see that with one solar power satellite, in an hour of direct sunlight, our solar power satellite would easily offset the CO2 footprint associated with 1 gallon of petrol. 4 solar power satellites using gallium arsenide solar cells in an hour could also offset the CO2 footprint generated by a person in 1 month. In the case of using silicon solar cells, again, you would need about 8 solar power satellites. Finally, you can see that if you were to build 8 solar power satellites using gallium arsenide solar cells, in 1 hour of direct sunlight, you'd be able to offset the CO2 footprint generated in a day by an average 1 megawatt natural gas plant. In conclusion, it can be seen that by building one of our solar power satellites, it would cost about $363 million. The total CO2 footprint associated with this would be about 1,600 metric tons. Depending on the solar cell used, you'd be able to generate 100 kilowatt hours of power and offset about 40 kilograms of CO2 per hour if you use silicon solar cells. Or in the case of gallium arsenide solar cells, you'd be able to produce about 220 kilowatt hours of power and offset about 90 kilograms of CO2 per hour. All things considered, if you want to offset the CO2 footprint associated with building one of our solar power satellites, it would require about 9 years using silicon solar cells, or 4 years if you're using gallium arsenide solar cells. With the average life of a solar cell being about 20 years, by building the recommended solar power satellite using our builder concept, either solar cell seems feasible of producing a negative CO2 footprint in the long run. Moving forward, while this presentation does show one potential concept for how a solar power satellite could be built and a case in which it would prove to be beneficial, many next steps are needed for proof of concept. In our case, we as a team are now focusing on 2 major areas, one being the use of LEO solar power satellites and exploring optimal orbit trajectories and how many LEO solar power satellites would be needed to provide constant energy to a specific key location on Earth. The second area being the actual spacecraft design used in modular development of these solar power satellites. Specifically, how can we use electromagnets for building these large space structures and transferring energy wirelessly, as well as increase the mass to surface area of our builder satellites so that we can build large satellite arrays using fewer rockets. And with that, I'd like to thank you for your time.